Hi, my name is Thilo Krachenfels and I will present our work entitled Automatic Extraction of Secrets from the Transistor Jungle using Laser-Assisted Side-Channel Attacks by Tuba, Kiyan, Shahin, Tajik, Jean-Pierre, Seifert and myself. Our work shows that secrets stored or buffered in on-chip memories can be extracted without knowledge about the chip's layout. On modern systems on a chip, tamper and read-proof non-volatile memories are used to store the root of trust keys used, for instance, to initialize secure boot. These non-volatile memories are expected to be secure against side-channel attacks such as optical probing and even against destructive reverse engineering using, for instance, a focused ion beam. However, while the key is used, it will be loaded into some CMOS memory cells or buffers. And also encrypted application keys will be contained in some kind of volatile storage after their decryption. At the same time, during the recent years, it has been shown that the memory content of on-chip memories can be extracted using sophisticated techniques known from IC failure analysis. Corresponding techniques are thermal laser stimulation and laser logic state imaging. The problem is that chip vendors believe that finding the key using these techniques is like looking for the needle in the haystack. They seem to think that the design complexity and potentially high reverse engineering costs are a natural barrier against attackers. Hence, the goal of our work is to demonstrate that the secrets can be extracted from the on-chip memories using laser-based techniques without the need to reverse engineer the chip's layout and memory mapping, and in an automated fashion. The remainder of this talk will be structured as follows. I will first present the necessary background knowledge on laser-based logic state extraction, and afterward I will talk about our approach, the experimental setup, and the results of our experiments. As I already said, we were using techniques known from IC failure analysis, where the chip backside is scanned with a laser. And the laser light can enter the silicon due to its wavelength of above 1.1 micrometer. The two techniques used in this work are thermal laser stimulation, where the laser irradiation causes heat generation in the chip, which corresponds to number 1 in this figure. So the laser irradiates the chip through the silicon backside. And the second technique, laser logic state imaging, is an optical probing technique where the reflection of the laser irradiation is captured and evaluated. And that's possible because the reflected light is influenced by electrical properties on the chip. And this corresponds to numbers 1 and 2 in this figure. Here on the right hand side you can see a CMOS memory cell which consists of two cross-coupled inverters. Depending on the bit state, the cell holds either top right and bottom left, or top left and bottom right transistors are conducting, corresponding to bit state 1 and 0. And the trick for laser logic state imaging is to modulate the supply voltage of the transistors, which can cause a modulation of carrier concentrations in the transistor's channels. And this in turn causes a modulation of the laser light that is reflected from the chip. And because the carrier concentration for conducting and non-conducting transistors is different, the transistor's logic state can be extracted. And the result of one LLSI scan over the chip is a grayscale encoded 2D image containing the logic states of the transistors. And also, TLS is similar. Here we also obtain 2D grayscale encoded images. But as a matter of time, I have to omit the background on thermal laser stimulation. But to summarize, we had two techniques at hand to capture the state of on-chip memory cells. For our approach, we used these techniques to capture images from on-chip memories, which we first filled with randomly chosen keys or secrets, and the images are then stored along with the secret. Then in the second step, we trained neural networks with the obtained dataset. And if the training succeeds, that already means that the secret can be extracted in an automated fashion from the automatically captured images. And then in a optional third step, a potential adversary might use the trained networks or models to extract the secret from the target device by capturing only a single image. For conducting the measurements, we used a FIMOS 1000 failure analysis microscope from Hamamatsu, which is equipped with different lenses and also light sources to conduct TLS and LLSI. Furthermore, it contains an interface for controlling the measurements in an automated way. Then, after capturing the image database, we trained convolutional neural networks on the images. We chose CNNs as image recognition techniques because they are widely used and also the manual tuning effort is minimized, which was precisely fitting with our goal to show that no manual reverse engineering effort is necessary. And that is also the reason why we only tried very fundamental CNN architectures in our experiments. Of course, one could potentially also use other classical machine learning techniques to extract the key bits from the images. We demonstrated our approach on 3 different targets. The first target was the dedicated key memory on a recent Xilinx ultrascale FPGA used for storing the bitstream decryption key. And what you can see here are the laser reflection images, or also called optical images. The second target was a 1 kilobyte SRAM of a MSP430 microcontroller, and as third target we chose the flip-flops of an Intel Cyclone 4 FPGA. From all these targets we captured automated measurements, and depending on the captured chip size, capturing one image ranged from 2 to 13 minutes. We made the entire dataset available online to give other researchers the chance to improve the key extraction from the images using other machine learning techniques. Here you can see a TLS image of the 256-bit key memory on the Xilinx FPGA. You can definitely see where the SRAM cells reside, since some of the image parts stay stable and some do not change. So these 2 blocks have some flickering bits, so that seem to be the SRAM cells, and the rest stay stable of the image. For the microcontroller's SRAM, that becomes a bit harder to observe. We programmed 512 out of over 8,000 bits in the SRAM while keeping the rest of the memory zeroized. But if you take a closer look, you can see that only specific lines are changing on the images, for instance here, here, and here. However, if the entire memory content is randomized, the whole image is flickering around and you cannot see in which area the key memory cells reside. So let's go to our results. So in the first experiments, we fed the full images into the CNN and tried to extract a single bit of the key. And already after a few training epochs, the key bits could be predicted reliable. Therefore, we tried to learn multiple bits in parallel using one network. For this, we added 1 output neuron per bit, and in the experiment shown here, the accuracy of 4 bits is plotted. So we observed that the achieved accuracy decreases with the number of bits that should be learned by one network, maybe because the capacity of the network was too small. However, if we give only a cropped section of the images into the networks, more bits can be learned in parallel. So we used, for instance, 64 by 64 pixel sections like indicated here. The drawback is that since some bits might not be contained in the cropped section, multiple training runs on all image sections will become necessary. But the advantage of sectioning the images is that we also learn something about the memory mapping of the device. Here you can see the bit indices and their corresponding image section. And this information can be easily obtained by training a network on all bits of the secret and observing the model's performance. So yeah, one can see that bits that are contained in the image section can be clearly separated from bits not contained in the image section. So all bits contained in the image section, go towards 100% accuracy, and the others stay, at around 50% accuracy, so they are not contained in the image section and cannot be learned from the images. As a matter of limited time, I cannot present further results from the other two targets, but I can say that we could successfully learn the key also from the microcontroller SRAM and the FPGA's flip-flops. This already leads me to the conclusion. So to summarize, hardware attacks using sophisticated failure analysis tools are often seen as too costly and time-consuming to pose a severe threat to modern ICs and SoCs. However, in this work, we have shown that the automation of failure analysis tools combined with deep learning techniques reduces the required effort by an adversary significantly. Hence, a great deal of attention has to be paid to this threat when designing new root of trust devices for critical applications. Thank you very much for your attention.